Good afternoon, everybody. Welcome to Wednesday afternoon of chemistry with your host, me, Dr. White. That's Chem 170, organic chemistry. Now, I hope you all have had a good day yesterday, and it's time. Ooh, I better fix that. I better cut that off later on. But anyways, got to buy some hairspray. That's organic chemistry too. All right, let's get going. We're talking about esters. And I don't know about you, did anybody happen to this last spring, or if you happen to go into a florist shop, you go around and you smell the flowers, that's because of esters. Or if you smell and taste many vegetables and fruits, like a banana or a pineapple, like that, you're smelling and tasting an ester. Oh, one other thing. Anybody happen to pick up a bottle of vinegar and say, ooh, it's got acetic acid, which is a carboxylic acid? You should. Or do you happen to pick up a bottle of ketchup, mustard, or relish? Look at, oh, it's got vinegar in there. That too has acetic acid, a carboxylic acid. Or did you happen to look at nail polish remover, ethyl acetate, and ester? Remember, organic chemistry, all chemistry is all around you. I stole that from SpongeBob, and it won't hurt you to think about it outside my lectures. Trust me, I'm a chemist. Did that work? How about trust me, I'm a doctor? Did that work? I'm both. All right, let's get to work. All right, on Monday, I talked, well, let's just back up a little. Hope you didn't get too dizzy. We went through how do you make an ester. Remember, an ester is a R group to carbonyl, carbon double bond oxygen with an oxygen, and on that oxygen we have R prime. This is an ester. And on Monday, I think, and last Wednesday, I talked about how you can take a carboxylic acid, react it with an alcohol, acid catalyst to make an ester. Now, on Monday, we found out that there's acid hydrolysis of an ester. And if you take an ester, react it with water and an acid, you get back the carboxylic acid and the alcohol you would have used to make that ester. And we're going to come back to this reaction later in the semester because this is how your stomach breaks down fats and oils you eat. How about that? Bet you didn't know you're a walking organic chemistry chemical plant in your stomach, and we'll go over that in the end of the semester, not even the last couple of weeks, how various chemical reactions that you've learned about, general reactions, are used by Mother Nature in your stomach to break down different food groups. You know, the key ones like beer, alcohol, no, pizza, potato chip, those food groups. And I started talking about saponification of an ester, and I went through, and let's pick up here, the following reaction. If you take an ester, react it with water. Now here I have sodium hydroxide. Well, let's go to my whiteboard. And I expanded it when I talked about it on Monday. If you take an ester and react it with a base, MOH, M can be sodium hydroxide, Na, lithium hydroxide, Li, or potassium hydroxide, KOH. And I hope you all know H2O is water. And what you get is not the carboxylic acid, because you do get that, but immediately in the presence of base, it forms the carboxylate anion. But you do get back the alcohol. So don't forget, you do not get the carboxylic acid you would have used to make that ester. You get, and I made a mistake. Don't look, don't look, don't look, don't look. It should be M plus. And you get the carboxylate anion, not the carboxylic acid. If you put down the carboxylic acid, I'll mark it wrong, because in the presence of any base, the carboxylic acid reacts faster than I can go like that, faster than you can blink your eye. And that's that. All right, now we did some, but let's do a couple more. Oops. Let's try that again. Hope I'm not having a bad arrow day. That wouldn't be good. All right. Why don't you let me bring this not off in left field there, but bring it closer. Why don't you do that reaction? What would be the organic product or products for the following reaction? 3 points each. And test number 3 will be like test number 2. We'll have general knowledge, nomenclature questions, and reactions. And when you're done, don't forget, give me a thumbs up. Thank you. And thank you. My turn. And how do you do this? You look for what's different, what's not carbon, what's not hydrogen. Get your attention like that. Oh, I've got 2 oxygens to the same carbon. One's double bonded, one's single bonded. On that carbon, there's carbons R, and the oxygen, their carbons, I'll call R prime. That's an ester. I'm reacting with, lithium hydroxide. That's a base, which I can write like this, and I have water. Remember, M can be sodium. In our case, it's lithium, or potassium. It can be a lot of other things, other bases, but for this class, I'll keep it to those 3. And what you get back is not the carboxylic acid, but the carboxylate anion of the carboxylic acid you would have used to make that ester, plus the alcohol you would have used to make that ester. Well, what's our methyl? What's our prime and propyl? Therefore, the carboxylate anion would be this. Not the carboxylic acid. And what's M? Lithium. And R prime, 3 carbons. Remember, you don't break carbon-carbon single bonds. And I should mention the bond in R prime with the oxygen here, the bond with R prime and the oxygen here will be the carbon, what I said about will be the carbon with the hydroxyl group there. So notice the N carbon has the oxygen there. Therefore, the N carbon will have that. And those are the two products you get. All right, on test 3, like test 2, where's my brain going today? You'll have a couple of synthesis problems. And the question would be, what would you react with sodium hydroxide and water to make those two compounds? If you look at the syllabus, we're right on track, which is a good thing. Very good thing. Thank you, Andrew. We'll give everybody time to finish. Everybody's finished. So it's my turn now. All right, how do you do this? Well, you look for what's different in the products. What do we have here? We got a benzene ring, but benzene doesn't react with sodium hydroxide or water. So I'm going to call that R. Got a carbonyl, oxygen minus, and sodium Na plus, which I'll call M plus. And then this right here, oxygen with a hydrogen and a carbon, that's an alcohol. And what do you react in here? Sodium hydroxide is a base, MOH, water. Remember, M can be sodium, which in this case it is, lithium, or potassium. And what do you start with? An ester. And if I come back to my products, I'm going to call this benzene ring R. This, my alcohol carbons are my R prime. And now I can go and draw my ester. My R group is a benzene ring. Don't forget the bonds in the center. Carbonyl, oxygen. Now, the carbon with the hydroxyl group here will be the carbon in R prime this oxygen is bonded to. And notice that's the middle of 3 carbons, an isopropyl group. And there are 4 bonds to carbon, so I can put in my hydrogens, and that's what you would start with, react with sodium hydroxide and water to make those 2 molecules. And it turns out when we get into fats and oils, I'll show you how our ancestors, and even to this day we do it, make bar soap. And I think you're all familiar with the stuff. You go like this with the bar to get your hands clean. Oh, coming attraction. How soap works on your hands. Guess what? That's organic chemistry, and I'll teach it to you. All right, any questions? All right, let's move on. Now, one of my all-time favorite reactions, why? Because it involves a Grignard reagent. If you take a ester, and one of the things I made a mistake here, not for me, but for you, at my level, we don't put the 2 in. At your level, I will. And if you reacted first with 2 molecules of a Grignard, second step acid and water, you'll make 2 molecules. Now, let me first of all put in the carbons here. And let me rewrite this on my whiteboard so it's easier for you to see. Am I nice or am I nice? Don't answer that. You don't have to answer that. You know. All right. And here's the reaction. If you take an ester and react it with 2 molecules of a Grignard reagent, remember X can be chlorine, bromine, or iodine, you get 2 products. Now, the first one is where you make not 1, but 2 carbon-carbon single bonds, something very special, very rare. And you get an alcohol. But this is a way of making not 1, but 2 carbon-carbon single bonds to new carbon. And then from the ester, this OR gets kicked out as an alcohol. So this is a great tool to make bigger molecules because you put on not 1, but 2 R triple primes. So let's take a look at this. Now, generally, you keep R prime small on the ester because you can distill it off, remove it easily from this is the product you're really shooting for. I always forget that too there because at my level, organic chemists know it should be there, but we're lazy and we don't put it there. So we look at this, excuse me, we have an ester. And I'll call this R and this R prime. If I look here, I have a Grignard, and I'll call this methyl group R triple prime. And the general reaction we have the Grignard, where X can be chlorine, bromine, or iodide. Second step, acid and water. Keep your eye on the carbonyl carbon here. What's attached to it is still attached to it. You have an OH group, an alcohol. Then you make not 1, but 2 carbon-carbon single bonds from the 2 Grignards. And then this part becomes an alcohol also. So if I look up here, my R is 2 carbons. This carbonyl will now have a OH, and then attached to it are my 2 Grignard, CH3, CH3. And you've made a much more complex molecule in one step, which when you need a complex molecule like that, this reaction gives you the tools to do that. Now, one of the things I neglected to do up here, which I won't now, how does this happen? And what I'm going to write, you do not have to write down, but Dr. White's going to have some fun. Dr. White's fun. When the first Grignard reacts with the ester, it attacks the carbonyl carbon just like it would in a ketone, and then kicks this OR out, minus out. And what you get this. Now, this is a ketone, and you learn a Grignard, the second one, and second step acid and water will attack the carbonyl carbon and put on the second R triple prime. Now, when you add the acid and water, this is an alkoxide, which is a base, and acid and water will convert it into this alcohol. And I just had a lot of fun. Thank you. But this is the mechanism. Unfortunately, because we only have one semester, I really can't go into mechanisms. If it was a 2-semester, we would, and I put mechanisms on the test. Relax, take a deep breath. They'll never be on my test, but organic chemists have have ways of finding out how things go step by step. And that's a mechanism. Part of my PhD thesis was to elucidate, that's a fancy word for meaning figure out, the mechanism of a reaction called the double Michael reaction, which I did. It was a lot of work, but I did. Oh, it was so enjoyable to succeed at that. All right, let's have you try one. Test, I'm going to be nice. I don't have to, but I will. I'll put a plus sign there. That means you get 2 products. So it's your turn to have some fun. How do I look? I got a new monitor. Do I look any better? Oh, that would be the camera. Actually, a friend of mine had an extra monitor like the one I have, and he doesn't use it anymore and gave it to me, and it had a lot less hours use on it than mine. Thank you, Andrew. And we'll wait for everybody to finish, because that's the polite thing to do. Have you noticed I try and always be polite? Well, you should. My parents trained me well. In fact, sad thing, over the years, I've heard students say they like me for one reason. I'm always nice to them and don't yell at them. I said, why should any faculty be mean to a student and yell at them? Unless they throw something at you, then I'd yell at someone, but nobody has ever done that. All right, let's get to work. How do you determine what's the product or products for a following reaction? You look at the starting material. And right here, materials, carbonyl, oxygen to that same carbonyl carbon. Carbons on the oxygen, R prime, carbons on the carbonyl. I'll call that, well, I didn't call it, it's an ester. Then, what are we reacting it with? Ooh, 2 of carbon magnesium chloride. That's a Grignard. Second step acid, H plus, water. And what you get, keep your eye on the carbonyl carbon because that's where the fun is, and it is. You get what's attached to the carbonyl carbon. R is still there. This new carbon here will have an alcohol on it. And from the Grignard, we do that very special, wonderful thing. You make not 1, but 2 carbon-carbon single bonds. And then this part here is kicked out and becomes this alcohol. So if we come up here, that's R and R prime, and the Grignard, this ethyl group, is R triple prime. And based on that, R is CH3, this carbon with the hydroxyl group, then my 2 R triple prime are ethyl, and my second alcohol, R prime, is also ethyl. So I get ethyl alcohol or ethanol. And the key thing you're really trying to make is this alcohol. Notice, starting with a simple ester and a simple Grignard, I've made a very complex alcohol. And alcohols can be used to make other esters, as you learn. And where are those used? Well, perfumes is one of them. Oh, this was fun. Oh, before I go, it's time for a little gift from Dr. White. Remember, little gift. How about little gift? And that is on test number 3 and the final. I will never give a synthesis problem with this reaction. On test 3 and the final, I will never give a synthesis problem. That's cruel, unusual punishment. I don't have to do that in my class, and I don't. Oh, let's do another one. These are fun. And the question would be, if you do that reaction, first step reacting this right here, I'm not going to give away what this is, with this right here, second step acid and water, what do you make? Your turn to have a lot of fun. Thank you, Andrew. And we'll wait for everyone to finish, including all of you in YouTube land who are watching this later today, or tonight, or tomorrow. Speaking about tonight, don't forget, if you have any questions, I'll have my office hour tonight on Zoom from 6 to 7:15. Stop on by, and I'll answer any questions or provide any help I can. All right, my turn. And the question is, how do you do this reaction? Well, you look for what's different. And this one, oxygens. Carbonyl, carbon double bond oxygen, and oxygen here, carbons on that oxygen I'll call R prime. Under carbonyl carbon, carbons R. Then if I look here, a benzene ring, well, for this reaction, a benzene ring alone will not react with an ester. But I've got magnesium chloride, that's a Grignard. And there are two of them. Second step, acid and water. And remember, X can be, in our case, it is chlorine, bromine, or iodine. And the two products you get are two alcohols. The first one, the R to this carbonyl carbon still attached, will become an alcohol, and you make from the two Grignards carbon-carbon single bonds, something very special, very rare. And then from this part, you'll get this alcohol. So if we go back up here, here's my R group, here's my R prime. And then the R triple prime is this benzene ring. And yes, you can make that Grignard. Therefore, the first product, the carbon here, is this carbon. What's attached to it? Are two carbons, OH. And then the fun part, you'll have two benzene rings. One, two. And then the second alcohol, the R prime, comes from here. And there you go. Oh, wait, ooh, don't look. I forgot the hydrogens here. There are 4 bonds to carbon, so I know how to put my hydrogens in. Now you can look. All right, now if you look at this alcohol right here, this is a really sophisticated, complex alcohol. And I have no idea how to make that other than using a Grignard reagent. You can't, well, I mean, maybe there is a way, but by using a Grignard and an ester, it's simple. All right, any questions on this? Again, I will never, that's my little gift to you. Actually, it's a nice gift. I will never put a synthesis problem with this reaction of an ester with 2 molecules of a Grignard, second step acid and water. All right, let's continue on. Now, one of the things I've done in this class to help you out and make your life easier is keep one, except for one exception we did in ketones and aldehydes, you only have one functional group in a molecule to deal with. But in real life, you can have molecules that have more than one functional group in them. And let's look at an example. Now, I'm going to turn the switch, click. Will this be on a test to the off position? But I think you'd be interested in it. There's something called polyesters or polymer esters, and they're also called really polyesters. Poly means many, and esters, well, you know what that is. So this is a way to make a molecule with many esters. Now, if you look at the first molecule, this has not only one, but 2 carboxylic acids. One here and one here. It's got a benzene ring. And here we have ethylene glycol. And that has 1, 2 alcohols in there. And let's go to my whiteboard. And what I'm going to write on here, you do not have to copy down, because the switch is click off. Will this be on a test? And one of the things I noticed I forgot on this slide, was acid catalyst. If we look here, really what we have here is a carboxylic acid and alcohol. Acid catalyst, and you make an ester. So if that happens, you'll make this molecule. Now, if you have more ethylene glycol present, and acid, again, this carboxylic acid, this alcohol, will react in this same reaction to form another ester. Again, don't write this down. We're in a classroom. I'd be telling you the class what I'm doing on the board. You don't have to write down. Now, if we look at this molecule, at this end, we have an alcohol. And I can react that with more terephthalic acid in the presence of acid catalyst. And this alcohol, or it could be this alcohol, that's an H, can react to form this reacts with that. My benzene ring looks awful, sorry. This new molecule. Now, if you have more terephthalic acid, this will react to make an ester. On this side, more ethylene glycol will react. It keeps on going and going, like the Energizer Bunny. Bang, bang, bang. Oh, I do commercials. But anyways, this is called a polymer. How many of you have ever seen a long freight train with a lot of cars connect together, like the same box car, or cars? Now they don't have box cars anymore that often. You know, the trailer cars, and it's real long. Well, this is the same thing, and it can keep on going. And you can have where you have 1,000,000 carbons in there. Wow, that's a big train. But another way of drawing that, because there's certain repeating units, is this molecule right here. And right here, and notice we have this repeating n times. And in this type of reaction, to make polyesters, that can be up to 1,000,000. So these are really long molecules, polymers. And it's a polyester because the repeating unit, you have this. And this is an ester. Now, one of the things I keep on telling you is, why am I learning this stuff? What good is it? Well, the obvious answer is you want to get a good grade in this class because someone said you had to take it to get into a program or a school. Well, why learn about this? Oh, by the way, the name of this molecule, common name, would be poly, meaning many, ethylene from the ethylene glycol, terephthalate. Remember, ester dropped the IC and the word acid and add ATE. So this is polyethylene terephthalate. Polyethylene terephthalate. Wait, that's a lot to say. I'm thirsty. I'm going to hold on. My bottle of water. Polyethylene terephthalate. Polyethylene terephthalate. That's really making me thirsty from the water in my bottle. So why are we learning about this? Well, this is called polyethylene phthalate. It's also known as PET, and that's the material of this bottle. That's how you make things you use in your daily life. You have a water bottle, a pop bottle, the plastic that's used to make this is a polyester, and it's this polyester most of the time. So why are you learning these things? Why learn about esters? They're in your everyday life. Got you there, didn't I? I bet you didn't realize this is organic chemistry. Not the water inside, that's inorganic, but the material, this is a polyester. And the next time you look at things, plastics, I'll talk about more, my mouse. By the way, if you don't know about it, these are great mouse. Who makes it? The Razor Death Adler light. I've had this a couple of years now. Plus, it has a light that goes on and off. Is that wicked? But anyways, polyesters. They play an important role in our life by this repeating unit esterification to make that polymer. Oh no, guess what? We've got to the end of the chapter. What that means is next Wednesday, I will go through the carboxylic acid and derivatives problem set. Make sure you're keeping up. You've already learned from tests 1 and 2 why I call them practice problems. But I'm at the end of this chapter, and you know what it means? It's new chapter and new functional group time. Oh, my happy. But I see some people are still writing things down. Let me know when you're done. Don't forget everything you see on here. All right, you're done. You can get download from D2L. All right, let me close this out. Oh, I didn't even open that. Hold on. I've got to go open that file. All right, new chapter time, new functional group. Does everybody see chapter 11 and 13? Amines, amides, heterocyclic compounds on your screen? Well, before we do this, you're going to have to see me first. Here I am. All right, I have to warn you. If it looks like I'm having way too much fun this chapter, I am. Because for many years, I was the section head of an international chemical company that I was in charge of what was called process and product development for nitrogen derivatives in all of North America. And I dealt with my counterpart in Europe. And we did that. Actually, I also helped out in South America too. And I have 9 patents in this. So if it looks like I know what I'm talking about, which I do, and I'm having a lot of fun, which I will be, that's because this is one of my, did I talk about comfort functional groups in here yet? I don't know if I did or not. I should have. All right, have all of you heard of comfort foods? You know, if you're not feeling good and you want to feel better, eat something that makes you happy. One of my most dangerous comfort foods are either the Little Debbie cakes, the white frosting with the white stuff and frosting in between, the chocolate on the outside, white chocolate. That's dangerous. More dangerous comfort food for Dr. White, me, is the onion and sour cream Lay's potato chips. Open a big bag near me. I don't know what happens. They just evaporate like that. Well, I also have comfort functional groups. Yep, I'm an organic chemist. Now you know. And the two biggies, first of all, are ketones and aldehydes. If I'm not feeling good, I'll think about and do some reactions on paper, think about ketones and aldehydes. The other big functional group that's a comfort functional group are amines and some of their derivatives. And that makes me feel good too. And we're going to talk about that now. All right. Now, what's an amine? And I'll never ask this on a test, but it's an organic derivative. Derivative means made from, derived from ammonia. And what is ammonia? In case you forgot, this is ammonia, NH3. And an amine is where you replace one or more of the hydrogens with an alkyl group, a cycloalkyl group, or an aryl group. Aryl means a benzene. And I should remind you, nitrogen has five valence electrons, and it needs 3 more electrons to get an octet, 3 bonds more. But nitrogen has a non-bonding lone pair of electrons. That, on certain cases, can. Here's nitrogen, and normally it has 3 bonds to it, but it can have 4 bonds. Remember, carbon can only have 4 bonds. There's no exception. Nitrogen in a molecule can have 3 or 4. So that's something to keep in mind. So an amine is where you take the hydrogens from ammonia and replace them with R groups. Now, I'm going to switches off on this slide, but I'm going to use this terminology, so you should be familiar with it. There's something called the primary amine. And that's when you have one R group on a nitrogen, and this is a primary amine. Now you can have 2 R groups on that nitrogen, and this is a secondary amine. And then you can have 3 R groups. They can be the same or different. And this is a tertiary amine. Now, if you look up here, these 3 types of amines have only 3 bonds. Oops, got to do this right. 3 bonds to nitrogen. So notice 1 R group, 2 hydrogens, 3. 2 R groups, 1 hydrogen, 3. 3 R groups, 0 hydrogen. So 3 minus 1 equals 2. That's why there are 2 hydrogens. 3 minus 2 equals 1. That's why there's 1 hydrogen. And 3 minus 3 equals 0. And I just looked at the clock. Dr. White was having way too much fun. It's time to take a break. Let's take a 5-minute break. Come back at 1:55 or 1:56, depending on your clock, in about 5 minutes, and we'll continue. I'll see you in 5. I can get up and stretch. Let's get going. Sorry I was late. I was looking out the window watching my lawn service doing a great job mowing my lawn. My lawnmower died this year. And at my age, I finally figured, I don't have to mow lawns anymore. So I hired this guy and he's done a great job. All right, let's continue. And we're talking about one of my favorite areas, amines. And you can have a primary amine, secondary amine, and tertiary amine. Now, I rarely do this, but I will now. I didn't do it with alcohols. Oxygen, just to remind you, and this won't ever be on test, has 2 pair of non-bonding electrons, but nitrogen has 1 pair. And in amine chemistry, that can react to form a chemical bond. And we get what's called a quaternary ammonium salt. And here you can now have 4 bonds to nitrogen. But when that happens, since nitrogen is providing both electrons in that bond, it will have a positive charge. All molecules in nature have a net 0 charge. Therefore, you have an anion associated in a quaternary ammonium salt. Now, there are various anions, but for this class, I'll stick to halogen, where X can be chlorine, bromine, or iodine. And this is called a quaternary ammonium salt. And I should tell you, I'm a world expert in quaternary ammonium salts. And I'm going to try and be a good chemist and not use slang. This is the only time I'll use it. If you work in quaternary ammonium salts, you don't call them quaternary ammonium salts. We're lazy organic chemists, and we call them quats. And I have a number of US patents in quaternary ammonium salt technology. So I guess I know a little about this. And so you have a primary amine, secondary amine, tertiary amine, and quaternary ammonium salt. Now, I'll talk more about it later on, but one of the big uses for quaternary ammonium salts is fabric softener. If you use a fabric softener, the molecule that makes your cloth, your clothing soft and also anti-static is a quaternary ammonium salt. And quaternary ammonium salts, and I'll talk about it either today or probably on Monday, are also antimicrobial compounds, and they're used to kill things like in operating room, to kill microbes or whatever. Now I'm out of my league because I'm a chemist, not a biologist, but various quaternary ammonium salts have antimicrobial properties. And we'll talk about that too. All right, now, nomenclature. Good news. If you work in amines, almost nobody uses IUPAC nomenclature. So I'm not going to teach that to you. I'll show it to you, but they do use common names. And how do you do it? I have it here, but let me show you better on the slide. How do you do an amine common name? So how do you use common names? Name each R group on the nitrogen as an alkyl group. And then at the end, add the word amine. So if we look at the following molecule, question would be, what's the common name? Now in test number 3, I will be changing the nomenclature question. In the past, I've always said give the IUPAC name, but now since I'll have a nitrogen compounds there too, I'll have give the IUPAC or the common name. Both will be accepted. So here, what do we have? Well, you look for what's different. Ooh, and nitrogen. What's not carbon? What's not hydrogen? Nitrogen on carbons. Excuse me. This is an amine. Notice the R group here is ethyl. So the name would be ethylamine, the common name. Hold on, I got feather in my throat or whatever. All right, your turn. What would be the common name of this molecule? 3 points each. Thank you, Ignacio. We'll wait for everybody to finish. Everybody's finished. Thank you, Andrew. And we have what's different? Nitrogen. It's got carbons here. It's a primary amine. The R group is a T-butyl group. Now, there's something I need to show you. Let's look at the following amine. And this would be dimethyl, di meaning 2, methyl, amine. Now, what I want to show you is, this is one way of writing it, which I won't, because I'm a lazy organic chemist. Another way of writing the same molecule, notice there are 2 methyl groups on the nitrogen. So I can put it 1 methyl group in a bracket, put the number 2, and do this. These are the same molecule, but this is the easier way of writing it. And being an amine chemist who's lazy, me, that's the way I'll probably write dimethylamine. And what would be the common name of that molecule? Remember, di means 2, tri means 3. Thank you, Ignacio. Thank you, Andrew. And we have 2, what's CH3, CH2? Ethyl. This would be diethyl amine, which is a secondary amine. Now, the groups could be different, but let's try a different one. And why don't you try that one? What would be the common name for that molecule? Thank you, Andrew. Thank you, Ignacio. All right, what's different? Ooh, what's not carbon? What's not hydrogen? A nitrogen. And this is a secondary amine, even though I'll never ask you that. And how do you name it? Well, you can call it methyl, ethyl, amine. But since it's a common name, there's no rules about alphabetizing, or you could call it ethyl methyl amine. And let's do one more. And here's one more for you to do. Thank you, Ignacio. Thank you, Andrew. Now, what's different? What's not carbon? What's not hydrogen? Should get your attention like that? And the answer is a nitrogen. And notice this is a tertiary amine. 3 R groups. 2 of them are methyl, and 1 is an ethyl. So you can have dimethyl ethyl amine or ethyl dimethyl amine. Now, why don't chemists, organic chemists who work in this area use IUPAC names? It's harder to do, and we're lazy. Let me give you an example. All right. First of all, I'm going to ask you, what's the common name for that molecule? Thank you, Andrew. Thank you, Ignacio. All right, the common name, I have a methyl group and butyl. It doesn't matter which you put first, and I'll only write down one of them. Could be N-butyl methyl amine, or you could have had methyl and butylamine. Now, IUPAC, you find the longest chain that the nitrogen is on, and you name that as an alkane. And this will not be on the test, butane. Then, like an alcohol, you drop the E, but now you put the word amine, butanamine. Like an alcohol, which carbon is the nitrogen on? And that's carbon 1. You number from either end. Now, what do we have left over? This methyl group. Now, it's on the nitrogen. And this is different. And again, this won't be on my test or final. To show that methyl group is on that nitrogen, we use a capital N. That's why I'm always careful, smaller N versus capital, and that's N-methyl 1-butanamine, which is easier to come up with, N-butyl methylamine or N-methyl 1-butanamine. I'm going to say the first one, and that's why organic chemists use that. Again, the IUPAC And I have a slide for that showing that right here, what I just did. Now, I'll teach you later, when you have other functional groups, the amine group is called an amino group, and this will be important when we get into amino acids. But there's one other nomenclature I need to go through. That's my favorite, quaternary ammonium salts. Now, I'm always going to stick to the anion being a halogen. So how do you name this? The common way, which we'll use, all right, for a quaternary ammonium salt, right here, name each R group as the alkyl group it is, and add at the end ammonium halide. Now, what we mean by halide, for Br minus, that's bromide. For Cl minus, that's chloride. For I minus, that's iodine. And the halogen anion you put to the right of whatever's here, even though it's really bonded to this nitrogen by an ionic bond, not a covalent bond. And if we look at this, oh, a nitrogen with a plus charge and 4 different groups on it, 2-methyl and 2-ethyl, or 4 groups. And that has an anion too. It's a quaternary ammonium salt. And how do we name that? Well, since there's no alphabetical rule, you can start either way. I'll start dimethyl, diethyl, ammonium, and Br minus. Oh, someone was nice enough to write on here, it's bromide. So you name each alkyl group, then add ammonium halide, Br minus bromide, Cl minus chloride, I minus iodine. And it's your turn. What would be the common name for that molecule? Thank you, Ignacio. Thank you, Andrew. And if we look at there, what's different, what's not carbon, what's not hydrogen? Ooh, an iodine with a plus charge and a halogen. And it's got 4 R groups on there. It's a quaternary ammonium salt. And how do we name that? And it doesn't matter. Diethyl, dimethyl. Oops, sorry, I'm thinking about an example I already did. Hold on. Di, 3 carbons straight to the end carbon, and propyl, ammonium, and then the halogen is iodine minus, which is iodide. And that's how you name it. Now, there's one special quaternary ammonium salt that's a very good friend of mine. Yes, helped make me a lot of money, helped pay for my mortgage, a couple of cars, and that's the following. And also, I have a couple of patents dealing with this. Now, if you see right here, the R sub T, that stands for a tallow or tallow-alkyl group. And I'll teach you when we get into fats and oil, that's the alkyl group with a mixture of 16 to 18 carbons with and without a double bond. And you'll see where it comes from. So let's call that ditallow, dimethyl, ammonium chloride. And why am I writing this molecule down? Because until about 10, 12 years ago, which is not that long in the history of mankind, this was the only molecule used for a fabric softener. If you bought Downy, if you bought Snuggle, this is the molecule that you were really buying that did the fabric softening. And I worked for one of the 2 companies that were the only 2 companies that made this molecule in the world. So we were the 2 suppliers of this molecule to Procter & Gamble, which was Downy, and Lever Brothers or Unilever, which was Snuggle. And I can tell you this, having worked with the chemists at both companies, because we supplied them product, when there was a problem, I'd get a phone call. And the best fabric softener to use are the dryer sheets. It's much better to use those than pour the fabric softener in your rinse cycle of your washing machine. Why? It puts more quaternary ammonium salt, a fabric softener, on your clothes. Now, I will tell you this. Have you ever gotten towels that have been around for a while and they just don't absorb the water off your skin as well? Oh, it's broken. No, what happens is enough of the quaternary ammonium salt gets on the towel to block it from doing its job. Now, when we get into carbohydrates, I'll teach you about how towels work. I bet you didn't think that was organic chemistry. It is. But I will teach you how towels work. But I can tell you now. But first, this is thirsty work. How do you get older towels to be more absorbent? By the way, in the industry, fabric softener industry, that's called re-wet. The higher the better the higher the re-wet, the better things are, because it absorbs the moisture off your skin. And how do you get the old towels to work better? You wash them once or twice, and you don't use a fabric softener. What happens when you get too much on your cloth, like your towel, guess what happens? It doesn't absorb. Same thing with old shirts and things like that. Have you ever heard? Well, I'll get to it when we get into carbohydrates. So, you want your towels to come back like they're almost brand new in terms of absorbing water. Wash them a couple of times, do some loads, and don't use a fabric softener, either in the washing machine or dryer. And that's my advice to you. Now, switches in the off position, amines themselves, the shorter amines smell a lot like ammonia. You don't want to stick your nose in a bottle of certain amines because they'll knock you off your feet. In fact, at one company, we had new chemists say, here, smell this. And whenever we did that, the first week they were working, we made sure there were a couple other chemists standing behind them because they'd fall back. It would really knock you off your feet. When I joined that company as new chemist, I'd already worked with amines in high school, a summer job. So I knew they gave it to me. I went like this, and everybody started booing because they thought, oh, we're going to get this guy. And they didn't. Now, amines, because they can hydrogen bond. The nitrogen with a hydrogen can hydrogen bond, are solids or liquids at room temperature, unless you get to like methyl and ethyl and propylamine. Those are gases. But for the most part, amines and quaternary ammonium salts are liquids and solids at room temperature. If I look at the clock, I think it's time for our lab. So I better go open up the lab. We're going to get out early today because I'm on schedule, which is a good thing. Normally, if we were face to face, we'd have 50 minutes of lecture, and then you'd go do the lab for an hour and 50 minutes. But since we're doing the lab online, I can cheat and take some of the time. Oops, I got to open the lab. All right, today's lab deals with ketones and aldehydes, which you know about, but let's look at today's lab. Now, today's lab deals with ketones and aldehydes. And remember, this is an aldehyde. This is a ketone. And if we're face to face, I'd be telling you about that. Be careful, but there's nothing really to worry about. Now, the first experiment, we're going to look at the solubility of ketones and aldehydes in water. And how will we do that? You'll take some small test tubes, fill them about this much halfway with water. DI means deionized, which we have at ECC in our lab, which I teach this in. All labs have DI water, it's called. And then to each test tube, you'll add about 5-10 drops of the aldehyde or ketone to test. And there's two ways. One is, assume this pen is your test tube. You take the test tube, hold it firmly, go 1, 2, 3, don't tickle it, really hit it, and that will mix it. You never mix a test tube like this. Also, we have what's called a vibro mixer. And there are these motors with a disc on top. It's in a box. You can control it. And when you push the test tube down on this rubber disc, it goes like this real fast, and it mixes up the solution, which I put them out. We bought them a number of years ago, about 8 or 9 years, 7 or 8 years ago, and we use those. And what you'll do that, let it sit for a little while, and look, is it homogeneous, the same throughout, or are there two layers? If there are two layers, it's insoluble. If there's one layer, homogeneous, it's soluble. Now, here are the ketones and aldehydes you would test if you were face to face. Notice right here in this table, when you hand in the lab, draw the structures for the compounds in the table below. So that's the first thing you're going to do. Now, the odor, let's omit. It was nice, but the benzaldehyde you've already done, the vanillin you already did in the past. All right, let's talk about oxidation of aldehydes and ketones. And what does that mean? If you take an aldehyde and oxidize it with potassium permanganate solution, KMNO4, that's like the bracket O bracket you learned earlier this chapter on carboxylic acids. And also, I skipped it until we got to carboxylic acids. An aldehyde can be oxidized to give a carboxylic acid. Well, when the aldehyde is oxidized, the KMNO4 is reduced, and you make magnesium dioxide, manganese dioxide. And that, the potassium permanganate has a purple color. The manganese dioxide has what I call muddy brown. Think of taking some dirt and putting water on it, mixing it together. That's what manganese dioxide looks like. Now, I have a YouTube video. Let's take a look at this. Sorry about the commercial.
D'accord, tu me rappelles si je suis pas là.
The purple is magnesium dioxide.
Aldehydes are oxidized by potassium manganate 7 to the corresponding acids. As the reaction proceeds, the purple color of manganate 7 ions fades away and a dark brown precipitate of manganese 4 oxide is formed. Aldehydes are also oxidized by potassium dichromate 6 in acidic solution. The orange color of the dichromate 6 ions changes to green.
We're not going to do that, but let's go back, instant replay. notice here, and we'll just look at the test tube on your right here. See that purple color? That's KMNO4, potassium permanganate in water. And watch what happens when he adds an aldehyde.
Are oxidized by potassium manganate 7 to the corresponding acids. As the reaction proceeds, the purple color of manganate 7 ions fades away, and a dark brown precipitate of manganese 4.
Doesn't that look sort of muddy brown? This does to me. Anyways, that's what you'll do in this reaction. Now, what I didn't show you, which I will now, is if you have a ketone and you react it with potassium permanganate, which is purple, you get no reaction. Which means it will stay purple. Now, in the lab, what you would do is put about 1 to 2 milliliters of the potassium permanganate reagent. There's a little acid in there to help it work, so you don't have to, like they did in the video, put it over a Bunsen burner. Acid helps make it go quicker. And then you'll add about 5 drops of the compound to be tested, and you'll mix it. Then you'll wait about a minute or two and look in, is it purple or muddy brown? Now I give you the data. Benzaldehyde, that's an aldehyde, turns it muddy brown. Cyclopentanone, ONE ending, you know what that is, it stays purple. Now, to make this interesting, in the lab, there's a bottle labeled very cleverly unknown number 1. And you would mix it and find out the color changes to a muddy brown. And later on, you're asked to figure out what functional group is in unknown 1. And you use this knowledge up here to do that. Uh-oh, I gotta hold on. Time out while I do this. One second, I made a mistake. All right, everybody see part 4, cross-allo condensation. Now, in this lab, and I'll let you watch the YouTube on your own, have fun watching that, you're going to do a very interesting reaction. And that's called a cross-allo. Remember, the aldol condensation is this reaction. And I showed it to you for this, an aldehyde. Now, I had water. You can also use ethanol, which is a simple alcohol. And you form the enolate anion that attacks the other carbonyl carbon, and you form a carbon-carbon single bond. And this is the bond you form. Now, a ketone right here has two alpha carbons, this one and this one. Now, this aldehyde, benzaldehyde, notice the alpha carbon, you have to have a hydrogen on there to form an enolate. And this alpha carbon, no hydrogens, therefore, 3 dots, no enolate anion can form there. Now, the crossed aldo, you're reacting in two aldehydes with this ketone with base. I don't have here, but it's ethanol. And you make this really wild molecule. Now, you know I'm an organic chemist. How does this happen? Well, let's first go through the procedure. What you do is you take 1.3 milliliters of benzaldehyde, half milliliter acetone, 7.5 milliliters of ethanol in an Erlenmeyer flask, and you stir it. And then once this is out, you add 2.5 milliliters of 5% sodium hydroxide solution. And then you swirl it till you see crystals. And I'd show you how to use a Buchner funnel, and you would collect it, try it, and do a melting point. And that would be today's lab. Now, what I'm going to show you, you can download from the lab section for this lab in black, D2L, wrong school, D2L. But let me show you something, because Dr. White's going to have a lot of fun. Remember, this is an area I like. Now, this is called the mechanism. Pay attention. Notice here I have my two aldehydes. Everybody see that on the screen? Thank you. And acetone. Now, when you react it with sodium hydroxide, the key reaction is forming the enolate anion on the acetone alpha carbon, one of them. This now has an enolate anion. It attacks one of the aldehydes, benzaldehyde, to form this aldol condensation product. Crossed because it's between not the same aldehyde or ketone, but a different aldehyde with a different ketone. Now, one of the things I haven't taught you is when you can have what's called conjugation, double bonds alternating single, double, single, double, single, double, and so on, that makes a molecule more stable. And if you can lose a stable molecule to form conjugation, that will happen like that. And it does. And notice on the molecule we just made here, I have on this carbon OH, this carbon a hydrogen. Let's see. Hydrogen, hydrogen, oxygen. Two hydrogens, oxygen. That's water. And if I lose water between these two carbons, I'll form a double bond. What drives that? The double bond here in the ring will now be conjugated to the double bond in the ketone carbonyl, like here. And that happens immediately. I mean, whoop, it's done, even faster than what I just said. Now, this new molecule here has an alpha carbon here. And it can form an enolate anion. It does. And this attacks the second aldehyde. Remember up here, we started with two of these to one of these, and forms this aldol condensation on this side. And same thing, double bonds here, double bond here. If I lose stable molecule, OH here, H there, water, I'll form a double bond between there, up here, and this will be fully conjugated in a very stable molecule. And the key step in this reaction is the first one, the base reacting with the acetone, the ketone, to form this enolate anion. That's the key step. And then you collect it. One interesting thing, you see all the double bonds in the common name. This is called dibenzyl acetone. Benzyl is benzene ring CH, and that's why it's called dibenzyl, because there are two of them on an acetone, what used to be an acetone molecule. Now, all the double bonds are conjugated together, both rings through these in the carbonyl double bond. And double bonds can absorb certain colors of light. And when you make this, this has a really bright yellow color. Why? Because the double bonds are absorbing all the colors of the light in the room we're in, or if you're outside in the sun, except the colors that make up yellow. And this is interesting. And here are the questions. Number 2, about the odor, omit. And I've got only 3 questions. Don't forget, in table right here on page 1, draw in the structures. And with that, we're all caught up. We're on schedule. I just finished the lab. We're done for today. We're done for the week, unless you come to my office hour. Remember, next Wednesday, I will be going through the carboxylic acid and derivatives problem set. Things are going to start getting quicker, so keep up. Don't fall behind. That way, you'll keep on getting a good grade in my class, which is something I want to see, because it makes me happy and hopefully makes you happy. I hope it should. And with that, I'll say, gang gesund. Remember, that's Yiddish for going hell. With the pandemic and the, how should I say this sadly, the projections this winter, it might be bad again. I have another 2 weeks to wait until my 6-month period is over to get my next booster. Yes, I've gotten both boosters. That age group, you don't want to get COVID-19, but I'll say, gang gesund, going to hell. Goodbye now. I'll see you either in my office hour tonight or next Monday. Bye. I stole that from Granny and Beverly Hillbillies. Bye.